So in this tutorial I'll be talking about the timer subcircuit. So here is the list of inputs and the outputs to the timer. So you can see that at the output it generates actually two timer outputs, two timer signal. The timer 0 and the timer 1. The data out goes straight to the CPU. So this data in comes from the CPU. This is the timer chip select. This is the read or write. This is the particular address of the timer, the clock, the reset, and the timer clock. This is timer 0 and timer 1, their clocks. So I'll be going over straight to the logic scene circuit to show you the simulation of how this works. You can find the code on my website, also projectfpga.com/SOC. You'll see this code under the timer subsection. So this is what the timer subcircuit looks like. Let me show you the externally what it is. So this is it. It has so many outputs actually, but these are the only outputs that actually goes to the other subcircuits. So like I told you, we generate two outputs. These are the two major outputs, the timer 0 and the timer 1, and these are the timer clocks here, timer 0 clock and the timer 1 clock. So let's go inside this subcircuit and see how it generates the timer outputs. So this is what the subcircuit looks like. So let's talk about the different inputs and the different outputs. So this data in comes straight from the CPU. Is used to, just like I stated on the website, that is a software programmable timer. So this data in determines the resolution with which the timer is counting. So I already gave an example on the website where I did some calculation here. Okay, sorry, I did a calculation here. So I said if you are trying to get a pulse time for every 100 microseconds when the system clock is 25 megahertz. So we did the calculation and found out that 100 microseconds is equivalent to getting a pulse at 10 kilohertz. So at the end, when you go through this calculation, you will get this value here. So if you give this value to timer 0, that means you'll be getting 100 microseconds or a 10 kilohertz pulse at timer 0. So this particular value here is what should be coming from your CPU. When you do the settings, you should be putting that value here as your data in. Then the chip select would be on. The chip select is an input from the control logic. So you know there are other subsections like the IO port, the RAM, the UART. So this chip select, whenever it comes on for the timer, it means that the CPU actually wants to read or write from the timer. So every other subcircuit have its own chip select. So this particular chip select input comes from the control logic. So once the control logic selects it, it means that the CPU wants to communicate with that particular subcircuit. So you need to turn it on also from the control logic. So whenever it comes on, it means that the CPU is sending this data is the CPU data, is sending the CPU data to the timer. Then you have your read or not write. So whenever is on, it means that the CPU is reading. If it's off, it means the CPU is writing. Then you also have this address. This address bit is used to select which of the timers you want to communicate with. If it's 0, it means you are sending the data to the timer control register. If it's 2, it means you are sending the data to timer register of timer 0. If it's 3, it means you are sending to timer 1. So these resolutions are used during when the timing is going on. Then the data out is still this data in that comes after certain clock cycles, when you've actually chosen which of the timers you are communicating with. Then you have this is the clock, I'm actually using the Logisim clock, but for the signal I use this clock here. So then again, these are the timer clock. You know, the timer clock is not using the system clock, is using a pre-scale, just as I stated on the website, using a pre-scale of divide by 16 and divide by 64. So when you go to this site, I will explain 2-bit. So it has a divide by 16 and a divide by 64. So this is the clocking for timer 0 is the divide by 16. So clocking for timer 1 is divide by 64. So these are the counter for timer 0, and this is the counter for timer 1. So this is where the data counts and compares. Now this is the actual timer signal for timer 0 and timer 1. So whenever the data comes in, so let's take a process of how the timing works. So here, let's assume I want to get the 10 microseconds or 10 kilohertz, and I'm expecting to put in this figure as for the CPU data, and that is 111 100. Okay, so I'll go over to the circuit, then I'm going to type in 111 100. Then I'm going to turn this chip select on. Then this read write will be off. When it's off, it means I'm writing. So then again, I'm going to choose address 1. Now the address is 0, so you can see that it's actually communicating, the value is actually here. So but when I choose 2, I'm now talking to timer 1. So you can see it. So whenever I select the value here, it actually goes to the data out. So how does this work actually? So these are more multiplexers. These multiplexers here, all these are multiplexers. So what the first check is, they check the read write mode. So these 2 bits here determines the 2 bits CS and RW passes through this AND gate. So the AND gate checks 1 is the chip select on and is the read mode off. So once the read mode is off, like you can see that the AND gate here is a NOT signal here. So it checks if the read mode is off. So if the read mode is off, it means it's in a write mode. So once it passes through this AND gate here, it is able to turn on this multiplexer. But before turning on the multiplexer, there is another AND gate that is individual to each of the registers. So those AND gates checks another. What the second AND gate checks is, it checks to know which particular address this data is meant for, whether it's the timer control register, whether it's timer 0, or whether it's timer 1. So this is how it checks for it. So this address comes here. So let me highlight it. Now yes, it's highlighted. So it checks using a comparator. These are comparators to check the value of the address. So it compares. If is equal to 0, it turns on the multiplexer for timer control register. If it's equal to 2, it turns on this multiplexer for the timer 0. Then if it's 3, it turns on this multiplexer for timer 1. So this is how the data from the CPU is being fed into the timer register. So now is 2 is fed to timer register 0. So now from this timer register 0, each of the timer will come down and now compare here. So these other 2, sorry. Okay, then again you will notice that these 2 register, the 2 timer register, this is the two counter registers, this one and this one, are not being clocked from this common system clock. The clock inputs comes from their different timer. This is where the clock input comes from, and this one is where the clock input comes. So they do not come from this common clock here. So that is why I will show you in the control logic circuit only how these two timer clocks are being generated. I won't talk about the whole control circuit. I'll just show how the timer inputs are being generated. So these timer inputs here are what is used to clock these counter registers. So whenever those data comes here, so what it does is there's a comparator here. So if I'm clocking it, let me show you how I'm clocking this one. So you can see here that is incrementing. So once I'm clocking it, so there's a adder here which does the incrementing per clock cycle. So the same goes for timer 1 also, as timer 0 the same is timer 2. So watch how this counter increments while I'm clocking this. So if it counts up to the data from the timer register, so if this counter counts up to the timer register, this is a comparator that compares the value. It compares the value of the timer, which is this one, the value of this timer, with the value in the timer register. So this is timer 0. You can see that is comparing from this timer register, that value here. So whenever it gets to that value using this register here, it turns on this multiplexer and the counter resets to 0. Else it keeps incrementing using this adder block. So the same goes for timer 1. So and whenever it turns it to 0, the timer pulses. So the same for timer 1 also. So whenever it counts up to that number, the timer turns on. So this is how the timer works here. So the same for timer 0. So but there's just a little bit different from what is actually on the code, from what John Kent wrote. I made a little adjustment to get this my particular timer output, but I won't correct his original code. So but this is how the timer should actually work. He actually made the timer to be bit 7 of these counters. Like timer 0 will be bit 7 of count 0, and timer 1 will be bit 7 of count 1. But I think this is a better model. So whenever the counter counts up to the value in the register, so this line comes from the timer 0 register, and this line comes from timer 1 register. So it compares it from what is actually in the timer. So once they are equal, it turns on and does this reset, sets it back to 0. The counter continues counting again by incrementing by 1 all the time for this, and at the point when it's setting it to 0, that's when the timer comes in, the pulse comes in again. So let me quickly show you how. Okay, let me take this back and quickly show you how the timer clocks were being generated. That is when I stated about the divide by 16 and divide by 64. So this is the control logic. So I won't explain it in this chapter, but let me just show you the timer clocks. So this is the 24-bit counter. It just keeps counting up. It does nothing. It's just continuously counting, and the clock is the system clock, so it continuously keeps counting upwards. So the timer 0 is placed at bit 4. That is bit 4, and bit 4 is actually 16. You know, in binary system, if you skip bit 1 and shift to bit 2, is divided by 2. If you shift to bit 3, divide by 4. Shift here, divide by 8. Then the next bit, divide by 16. So okay, so let's assume this is bit 4. So if you are here, it's divided by 2. Then if you are here, it's divided by 4. Here is divided by 8, and this is divided by 16. Then the next one, the bit 5, is divided by 32, and the next one, bit 6, which is for our timer 1, is divided by 64. So this is the counter that does the upwards counting, which we use to generate our counter clock. So the full circuit connection shows how I actually selected it. You can see here. Sorry. Okay, this is it. So let me zoom in. So if you look closely, you find out that these are the counters here. This is 4 and this is 6, which goes to the timer clock. They both go to the timer clock. And if let me highlight where it came from. So you'll see that it's coming from that counter L from our control unit. So that's how this counter subcircuit works, and this is the top part. So we didn't need the registers. So what we needed was actually the 2 timers and the data out. Then the interrupt request was not used for the whole circuit because I didn't have any external place to connect it to. But the interrupt request is bit 1 of this data in when it's connected to the timer control register. So when you go to the code, you will understand more on it. So what I explained in here is exactly what is on the code. So thank you.